Alright, in this video I'm going to show you how to make an ideal transformer in LT-Spice. Sometimes, particularly in the problems that we've seen with transformers, we're not necessarily given the inductance values, so it's not trivial to make a coupled inductors model of the transformer in LT-Spice. You need something else. So the ideal transformer that we can make uses what's called a behavioral voltage source and a behavioral current source, and LT-Spice is perfectly happy making a transformer this way. So I'm going to show you how it works. So let's start by going to the component selector window, and I'm going to say BV. That gives me a behavioral voltage source. You can see it here, and I'll put one of those down on the secondary side, and then I'm going to also go in and hit BI, and that's going to give me a behavioral current source. Okay, and so this is going to be basically the primary and the secondary of my transformer. Okay, so I'm going to draw this just like this. Oops. I'll draw it just like this. And then I'm going to put a box around it so that we know that that's our transformer. So I'll go draw, rectangle. Yeah, I figured that would happen. Drag this around a little bit to make it look a little nicer. That's good enough. Okay, and so what we need to do here is we basically need to implement the transformer equations that we know. And basically the first one is that the voltage across the secondary is equal to the voltage across the primary multiplied by the turns ratio, right? So let's start by labeling our nodes on the primary side. We'll call this VP plus, I guess VP underscore P is fine. And then we can say VP minus right here, VP underscore M. And then on the secondary side, let's call it V secondary VSP and VSM. All right, so we're close to this thing being operational, but not quite. We need to put the actual functions into these behavioral sources. Basically what the behavioral source does is you can throw any old function in here and it will output a voltage or a current with that particular function. So for us, because we want this circuit to behave like a transformer, we need this secondary voltage source to output a voltage that's equal to the primary voltage but multiplied by the turns ratio. We'll call the turns ratio N. Okay, so let's just remind ourselves that N, the turns ratio, is equal to the number of turns on the secondary divided by the number of turns on the primary. Okay, so let's throw that there. And so for this, we're going to just say that I want this voltage to be equal to VP or the voltage at node VPP minus the voltage at node VP underscore M. Okay, all of that in parentheses. And then I want to multiply this by my turns ratio, which I'll just call N. Okay, let's just call it capital N. Okay, and then let's call this is just a comment, so for your information. This is just a comment. And so that's going to give me this voltage here multiplied by N, which I haven't specified yet. Let's just make N some parameter N, and we'll just make it 4 to 1, basically. That's what we have in the next example anyway, so let's just do that for now. So I'm basically saying I want this voltage here to be the voltage at the primary, but multiplied by N. Okay, and so then the last thing I need to do here is I need to make this current, right? The current at the primary needs to be the current at the secondary, but divided by N, okay? Or multiplied by N as well, because we're going from the secondary to the primary. So what I'm going to do here is I'm basically just going to say I of B1, basically the current through the behavioral source, or maybe it's B2. What did I put? No, that's B1. So I want this to be that current through the secondary, but I want that to also be multiplied by N. And there's one last thing I need to do in order to get this to work. Because I know that a current into the dotted terminal of my primary forces a current out of the dotted terminal of my secondary, I need to flip this current because the current is defined as the current flowing into the dotted terminal on this side, and I need it to be outward. So I'm going to make this a minus. And what I'm basically assuming is that my dots are in the top of both of these. Maybe I should even draw that. Let me say edit, or I'll just, yeah, edit draw, or how do I draw, and I'll throw some circles in here. So I'm basically assuming I have a dot here. Oh, wow, that's really ugly. Let me try that again. Draw, circle, that works, and then we'll just make it solid. So I'm basically assuming that my dots are here and here. Okay, we're ready to test this thing. So let's do it. Let's put a load out here. Just call it 1K. And then let's put a voltage source on the input, a voltage source with some sinusoidal behavior here. I have to ground this. I'm not sure if I have to ground this. We'll see, but I might have to ground both sides for this ideal transformer just because LTSpice might get mad at me. We'll go to sine, and then we'll say 0, 1 volt, and let's just give it a frequency of 1 kilohertz again. And I should expect to see 4 times the voltage on the secondary side. Okay, so let's run this. Let's go .tran. We'll go 3 milliseconds, and let's see if it gets mad at us. No, it looks like it's going to work. So let's give it a shot. I look at my voltage on my primary, and I look at my voltage across my secondary. And there it is. Okay, beautiful. So I add a plot pane here, and I can see that my primary voltage is swinging from 1 to -1. My secondary voltage is swinging from 4 to -4, and so I have successfully created an ideal transformer in LTSpice using behavioral sources. Okay, and this transformer has a turns ratio of 1 to 4. Basically, it's a step-up transformer. Okay, so I'm gonna go ahead and end this video. I know it's gotten a little bit long, probably taking up a ton of data on my Google Drive. But in the next video, we'll basically use this transformer and we will build the circuit of problem 11.23 and show that our hand calculations are correct.